shutter for 90 seconds, close it, move the telescope point in a different direction, open it for 90 seconds, close it. And so their individual exposures are 90 seconds. But as I said, over time, we come back and revisit each part of the survey field 10 times in each of the filters. So by the end of the survey, each part of the sky will be covered 900 seconds of equivalent exposure. Yeah, then we layer them on top of each other, called co-addition.
Thanks for the great talk. It seems like the total energy of the universe is increasing. If that's correct, what happens to the law of conservation of energy?
Good question. So that's true. If dark energy is the dominant stuff in the universe, as I said, when the universe expands, the density of dark energy isn't going down. So therefore, so the energy per unit volume isn't decreasing. If the volume is increasing, then the energy would be increasing. So what happened to the law of conservation of energy? It's not true. Sorry. And actually, we've known that for going back way. So in Einstein's theory of relativity, energy as a global quantity is not conserved. Left-hand side here.
Yes, at the beginning of your talk, you said the farthest objects are 30 billion years, 30 billion light years away.
Yeah,
how can that be if the universe is only 13.8 billion?
Yeah, I knew I was going to get that question. Good question. So it really comes down to how do we measure distances? And the point is, so we measure distances with rulers or tape measures or something, right? That clearly doesn't work when I'm talking about things very far away. And so there are different ways to measure distances. So depending on those different ways of measuring distance, I can use the brightness of an object, I can use the apparent sizes of objects, and those can give me slightly different answers. So the 30 billion years was using one particular measure of distance that doesn't mean that that anything moves faster than the speed of light. It's just due to the fact that when I get to very large cosmic distance scales, it takes a long time to measure that distance. And so depending on how you define distance, you can get different answers. No, it's not inaccurate. It just means that when I get to cosmic distances, when I tell you the distance to something, I also need to tell you which distance I'm using. And as long as I tell you which distance I'm using, it's fine. Trust me. Second row over here.
Over here. Here we go.
Yeah.
So the ratio between dark energy and just regular matter, did you actually get that by looking at the amount of matter that there is, figuring out how much energy you'd need to accelerate to match your observations, and then just do the energy equivalent of that, and then just take the ratio?
Yes, exactly.
You're kidding. We need to talk later.
That's it, exactly. Over here.
What's the difference between dark matter and gravity?
What's the difference between dark matter and gravity? Okay, so gravity is a force. It's an interaction. So gravity is anytime you have mass or energy, it creates a gravitational field, which exerts a force on any other body moving in that gravitational field. So gravity is the thing that dark matter causes, if you like. Dark matter is just stuff. It's mass. It's something that has mass that is dark. Beyond that, we don't really know what it is, but it's not in itself a force. It is. So in elementary particle physics, we have the basic particles of nature, the quarks. Those are the stuff that all matter that we see is made of. And then we have the interactions, the forces between them. And gravity, so we usually talk about the strong force, weak force, the electromagnetic force, and then there's the gravitational force. And so basically our picture of how physics works is that it's elementary particles interacting via forces. So dark matter we think is likely to be a new elementary particle, gravity is one of the forces through which they interact. Sorry, microphone?
Back here. I can repeat.
So the question is, does that mean that dark matter does not produce gravity? No, we think dark matter does produce gravity. Any form of mass or energy produces gravity. But it's just, it's not the same as gravity, which is what the previous question.
A little back up here.
How close is our closest galaxy neighbor?
How close is our nearest galaxy? Well, some of these very faint dwarf galaxies are only tens of thousands of light years away. The largest big galaxy to ours, the closest one comparable in size to the Milky Way, is Andromeda, and that's about 2 million light years away, give or take. Galaxies, the typical separation in space between large galaxies is a few million light years.
So if we were trying to send a deep space mission to the Andromeda galaxy and the universe is expanding at 3,000 miles per second,
okay, good question.
Wouldn't that put like you keep cutting the distance in half every time you never get there?
Yeah. Well, first of all, it would take a really long time. I know there's some people who are happy to go to Mars and not come back, but that would, anyway. Although actually, so with Andromeda, I can sort of give you an answer without actually answering, so I said all these galaxies are expanding, moving away from our galaxy, and that's true of almost all galaxies. It's true of all distant galaxies. Andromeda actually happens to be gravitationally bound into a pair of galaxies with the Milky Way. So actually Andromeda is approaching us. Andromeda and the Milky Way will collide and merge together in some number of billions of years. So actually, if you wanted to just go to Andromeda, then you could just wait a few billion years. But it's true, if you want to go to other galaxies, then yes, you have to go fast because they're moving away from us. But you can move faster. They're not moving faster than the speed of light, so we think you can get to them.
Left-hand side over here.
What's your favorite part of studying dark energy?
My favorite part?
Yeah. Why do you study dark energy? What got you started in it?
Oh, good question. Well, actually, what got me started studying dark energy was by training. I'm actually and there was indication back in the mid-1990s, before the supernova discovery, that things were not quite right. We already had sort of tentative evidence that this picture of a slowing down universe wasn't quite holding up. So it was sort of pre-evidence, if you like, for what we now know is acceleration of the expansion. And I had, in my earlier career, focused on, so I mentioned in one of the slides that we think there was actually a much earlier epoch of very rapid expansion called primordial inflation. So we think that a tiny fraction of a second after the Big Bang, the universe was also actually speeding up. And then eventually inflation ended and it went into a decelerating, a slowing down expansion until dark energy took over. So we think that this is actually at least the second time in cosmic history that the universe is speeding up. And I had worked earlier in my career on some hypothetical ideas for what could be causing that earlier epoch of cosmic speed up, inflation. And so with some colleagues here, we started thinking about, well, gee, what could that same kind of phenomenon, I mentioned this very light, super light cousin of the Higgs boson, could that be causing the current epoch of cosmic acceleration? So that's really how I got into this study. And then in the late 1990s, the discovery of the direct evidence for cosmic acceleration from the supernovae got me into thinking about, okay, how can we test this idea? How can we learn more about it? Theorizing is great. I love theorists. But there are certain times when you just need more data to really make progress in understanding something. And my judgment has been that in dark energy, we really need to do these kinds of surveys to point us in a particular direction of theory.
Thank you for sharing.
Third row here.
My question is related to your slide, which shows percentages of dark energy, dark matter, and normal matter over the course of 13.7 billion years. Now, the slide shows that originally there was 17% of regular matter. Now we have only about 5%.
Right.
How do you explain this reduction, or in the amount of regular matter? Where it appears?
Okay, so basically,
going to the faint.
so the universe is expanding, and as any kind of, if you have a gas that expands, right, it becomes less dense.